Hello friends, today's lecture we're going to continue with design procedure of retaining walls and application of lateral earth pressure theory that we discussed previous lecture to design procedure. And we will apply Rankine earth pressure theory. And in Rankine earth pressure theory, when this surface is inclined, having a slope alpha, then we will analyze stability, or we will check stability of this retaining wall against overturning, sliding, and bearing capacity. First of all, let us apply earth pressure theory and let us find lateral earth pressure applied to this retaining wall. The Rankine active condition is assumed to exist along the vertical plane A through B. In this picture, this is line, but you know, we analyze this retaining wall for one slice of continuous retaining wall. So this is actually a plane, a B plane. Rankine earth pressure equations may be used to calculate lateral pressure on this face. In analysis of the wall stability, is first PA Rankine, the weight of soil above the hill, and the weight of the wall itself, weight of concrete structure, will be taken into consideration. A similar type of analysis may be used for gravity walls. The same principle will apply. Remember that we have another theory, Coulomb theory. It's rarely used, but if you want to use, of course, this can be applied. The only difference between Rankine and Coulomb theory is the assumption of friction along the wall. In Rankine theory, we analyze only on this plane, A through B, and we assume friction angle between wall and the soil is 0. But in Coulomb theory, this friction angle is taken into consideration, and average values of this friction angle is given in this table. But in this lecture, we will focus on Rankine procedure. What kind of failures we can expect on retaining walls? A retaining wall may overturn about its toe, this point, due to horizontal pressures. Similarly, these horizontal pressures, earth pressure, may result in sliding. The wall may fail due to loss of bearing capacity, and it may undergo deep-seated shear failure, and also excessive settlement may be a problem for retaining walls. The checks for stability against overturning, sliding, and bearing capacity failure will be discussed here. And settlement is the same as the foundations, and It's the same as chapter 7. And deep shear failure can occur only or along the cylindrical surface. So this is related with slope stability topics. So in this chapter, we will deal with overturning, sliding, and bearing capacity failures. In overturning check, the moment equilibrium will take about this point C. For this overturning check, the only force which forced this wall to overturn is horizontal component of this PA. Horizontal component. But as you see in this figure, we have some resisting moments. Comes from its own weight due to backfill weight and even passive pressure, if it exists, of course, passive pressure in front of the wall. And the same principles apply for gravity or semi-gravity walls. And PA values for cantilever and gravity walls, PA and PP, are shown, and also nomenclature is shown in this figure. Active pressure, passive pressure, and please note that we will use soil properties where we analyze. For example, under the wall, we will use soil properties under this level. For above conditions, these soil properties will be used. Please don't confuse. And one more thing we have to remember, when we analyze sliding, cohesion and friction angle will be taken as values for this interface, concrete and soil. So it's given as C prime, phi prime here. And these values will not be the same as cohesion and internal friction angle of the soil. We will discuss in detail. And of course, we will apply some safety factors as a rule. And our safety factor for overturning will be equal to total resisting moment divided by summation of overturning moments. Actually, every overturning moment will be equal to, because reason for this overturning moment is horizontal component of PA, is pH, horizontal component. And where does pH apply? Because the distribution is triangular, 1/3 of the wall height, H prime over 3. And please note that H prime is not height of the wall only. We will add this portion if this soil behind the wall is sloped. It's H prime. To calculate the resisting moment, a table can be prepared because in resisting moment calculation, We have some complicated geometries, and to make easy this calculation, we will divide these geometries into basic geometries, triangles and rectangles. For example, this wall can be divided into 1, 2, 3 rectangle, second rectangle, and triangle. And the backfill can be divided into 2, 1 rectangle and 1 triangle. And all these areas, actually the volume, considering the width of the wall, these areas will result in resisting moments, and we will calculate resisting moments for every part. So a table will help you. The weight of the soil above the hill and the weight of the concrete, as masonry, for example, are both forces that contribute to resisting moment. Note that the force P sub V vertical also contributes to the resisting moments. I mean, this is a vertical component of PA, and it's equal to PA sine alpha. The moment of the force P sub V about C can be expressed as given here, P sub V multiplied by B. B is the width of the slab. Once this resisting moment is calculated, the factor of safety can be calculated as given here. Resisting moments for every portion divided by overturning moment. Let us discuss check for sliding along the base. The reason, again, for sliding off this wall is horizontal component, and resisting force is resistance is due to friction along this base. We can calculate this friction by using basic strength equation. Remember from shear strength. Normal force multiplied by tangent of friction angle plus cohesion, if exists, of course, if exists. But again, please note that these angles are not, this angle is not internal friction angle of soil. This is friction angle of this interface between concrete and soil. Similarly, this cohesion is not cohesion of the soil. This is adhesion between soil and the base along this interface. Thus, the maximum resisting force that can be derived from the soil per unit length of the wall along the bottom of the base can be expressed R prime and sigma prime times tangent of this friction angle, again B times adhesion factor. What does this one means? This is due to 1 meter slice of wall. B multiplied by 1 means B multiplied by length. B times L. Because we are analyzing this wall for one slice having 1 unit length, and actually it's 1 meter. So this is area multiplied by shear resistance. Yes. So B times normal stress should be equal to sum of vertical force, of course. So it can be rewritten as total force multiplied by tangent friction angle plus B times attachment factor if exists again. And passive force PP, again, I have to tell if exists. Sometimes this depth is negligible, and sometimes this PP can be neglected. But if we want to consider, PP should be added to resistance, because the direction of vectors are inverse. So this PP resists to this pH. Only horizontal force that will tend to cause the wall to slide is a horizontal component of active force, as I said before. So final equation for safety factor for sliding. Safety factor for sliding can be calculated using this equation. Check for bearing capacity. The vertical pressure transmitted to the soil by the base slab of the retaining wall should be checked against the ultimate bearing capacity of the soil. But as you expect, the stress distribution under the wall, under the base of the wall, will not be uniform. And Q at toe and Q at heel, toe and heel, are the maximum and minimum pressure occurring at the end of the toe. So we need maximum and minimum values to bearing capacity check. You are familiar from bearing capacity chapter. First of all, we need to locate the resultant force. So we need to determine X value. This is actually calculated from moment equilibrium using this relationship. And net moment will be equal to summation of resisting moment minus summation of overturning moments. We will use net moment here. And then we can calculate eccentricity value. This value is equal to half of the B minus this X value. This is eccentricity. So using our stress distribution equation, Qmax and Qmin can be calculated. Once the ultimate bearing capacity of the soil has been calculated by using bearing capacity equations, that was given in bearing capacity chapter. And once we determine this value, safety factor for bearing capacity will be equal to bearing capacity divided by Qmax. We will consider maximum value for bearing capacity check. Let us solve one example problem, 13.1. The cross-section of a retaining wall type is cantilever, and reinforced concrete. The parameters are given under the base and above the base. We will check factor of safety with respect to overturning, sliding, and bearing capacity. First of all, we have to determine this height value. Here it's given as AB plane, H prime. Because only wall dimensions are given, we have to add this portion. This is equal to 2.6 multiplied by sine what's the angle? Yes, 10 degrees. I'm sorry, that's tangents, 10 degrees. The other values are given. 6 meter wall height and 0.7 meter base height. The total H prime is 7.158. Because phi prime angle is 30, as given here, and alpha is 10 degrees. We can calculate active earth pressure, Ka, and it will be equal to 0.3495. Then Rankine active force PA can be calculated. These two angles will be equal, the surface slope angle and PA inclination. You can use 10 degrees again. PA is the area of triangle, and it will be equal to 161.2 kilonewton per meter. Per meter comes from the 1 meter length, unit length. We need to divide into vertical and horizontal components, P sub V and P sub H, just multiplying sine and cosine of this angle. So for moment calculations, we have to divide geometries into basic geometries: rectangle, triangle, rectangle, again triangle. 1, 2, 3, 4, 5 section. For every section, we will calculate area. Applying with unit weights, we will determine weight of this area, weight of this section. And we will determine moment arm, then calculate moment. For example, for section number 1. Section number, this rectangle. 0.5 multiplied by 6. Area is 3. Multiplying with unit weight is 18. The weight will be 70.74. We need to find moment arm because it's rectangle, and weight will apply at the center. 0.7, 0.7. Total is 1.4, 1.4 minus 0.25, and the moment arm will be 1.15. It's just here. For second section, the moment arm will be at one third of this dimension, this triangle. So moment arm from the point C will be 0.833. Applying the same principle for other sections, at the end we will have P sub V total vertical force, and finally summation of resisting moment. We will put these values to the equation. Then we can calculate overturning moment. Overturning moment is the pH multiplied by h over 3. But h prime over 3. What is h prime? The summation of, we just calculated, well, I'm sorry, yes, 7.157. Then overturning moment is 378. We just calculated summation of resisting moment, and dividing to overturning moment, safety factor is 2.98. This is a reasonable value, and we can accept. It's okay. Safety factor again, slide. The reason for sliding is horizontal component of PA. In other words, PA multiplied by cosine alpha. The resistance comes from internal friction angle or friction angle of concrete soil interface and adhesion along this interface, plus passive pressure in front of the wall. Do we have? Yes, both we have friction angle and cohesion, so we can put here. But let me repeat again. These are internal friction angle and cohesion of soil. These values cannot be used as resistance of this interface, because this interface is between concrete and soil. So we need to determine friction angle along this concrete soil interface. Similarly, adhesion along this concrete soil interface. Of course, these two values are related with soil properties. Then we will multiply a correction factor or a coefficient K1 and K2 to convert these soil properties to interface properties. Generally, these factors are taken as 2.3. In some books, you can see as 0.7 or 0.75. These are close values. Here, in this book or in this lecture, we will use 2.3. 2.3. What else? Yes, we have to determine passive pressure using this equation. And just putting known values here in safety factor equation. The safety factor is 2.73, and for sliding check 1.5 is satisfactory. The result is greater than 1.5, and it's okay. And we need to determine bearing capacity factor. To check bearing capacity, first of all, we need maximum and minimum pressures and ultimate bearing capacity of soil to compare them. You know from bearing capacity chapters, first of all, we need eccentricity. Eccentricity is 0.4. Then using eccentricity value, because we know total vertical force and total, base dimension, these two are known. Just putting E value here. For minimum, use plus. For minimum, use negative, minus. So maximum and minimum base pressures are 189 and 45 kilopascal. To calculate bearing capacity, of course, we need this N and F factors. They are given in your textbook as table, and you can determine these values and F values. Then finally putting all these coefficients and soil parameters, ultimate bearing capacity is 569.22. What is bearing capacity? This is the ratio between ultimate bearing capacity and maximum stress under the base. It's 3 and it's acceptable. One other variety of retaining wall is mechanically stabilized retaining walls. This is somehow soil reinforcement, or we can call it as ground improvement technique. Sometimes it's accepted as retaining wall construction methods. Anyway, in mechanically stabilized retaining walls, by the way, it's very popular in our country, in Turkey. For example, in Burdur Highway, when we go to our main campus, retaining walls of these highway bridges are made of mechanically stabilized retaining wall. In this method, reinforcement materials may be metal strips. For example, in Turkey, it's very common. Almost all of the walls are made of metal strips. We can use geotextile as reinforcement or geogrids anyway. These reinforcement materials are used to reinforce the backfill of the retaining walls. The backfill is granular soil. Gravel, sandy gravel. But it should be granular, not clay, not fine-grained soil. It should be coarse-grained and gravel-dominated, well-graded gravel. The advantages are the soil's increased tensile strength, because, you know, tensile strength of soil almost is equal to almost zero. And using this technique, the tensile strength is increasing. The shear resistance developed at the soil reinforcement interfaces. Use of free draining granular soil only avoids the effect of pore water pressure inside the soil, because gravel or gravelly soil with more groundwater. Perfect drainage material, actually. The design procedures can be divided into two parts. One is internal stability, two, external stability. By saying external stability, we mean the same procedure for concrete retaining walls. Check for overturning, sliding, bearing capacity, and also other checks, settlement, general shear. Anyway, what does internal stability mean? Determining tension and pull-out resistance in reinforcing elements, and ascertaining the integrity of facing elements. Internal stability means stability of this reinforcement and facing element as well. Reinforced earth walls are flexible posts. This is very important advantage when subject to earthquake forces. And their main components are backfill, gravel, and reinforcing strips, and third, a facing element, cover or skin on the front face of the wall. Very simple. You see here real pictures and schematic three-dimensional sketch. In most cases, precast concrete slabs are used as face elements. The slabs are grooved to fit into each other so that soil cannot flow out between the joints. The simplest and most common method for the design of ties is the Rankine method. Because we are familiar to Rankine method, it will be easy to calculate. The design actually is to locate these ties in three dimension, in vertical and lateral dimension. So we need to determine tie force. Tie force per unit length. Per unit length means, what does it mean? We are analyzing in two dimensions. Two dimensions solution is made for one slice of this wall. So we will apply 1 meter unit length for one slice. And tie force, capital T, will be equal to active earth pressure at any depth multiplied by area of the wall to be supported by the tie. If a rectangular facing element used, such as shown here, the area of facing element multiplied by horizontal earth pressure, active earth pressure, will be equal to tie force for every reinforcing element. The reinforcement ties at each level and thus the walls would fail by either a tie breaking or tie pull out. Tie breaking or tie pull out. The factor of safety against tie breaking may be determined as a safety factor 2.5 to 3 is satisfactory for breaking. Safety factor for breaking equals to breaking strength of each tie divided by maximum force. Resisting strength divided by breaking force. Strength can be calculated. Breaking strength of material multiplied by cross-sectional area. Cross-sectional area, WT. W width, T thickness, so it's cross-sectional area. And maximum tie force, as given above, active stress multiplied by facing element area. Reinforcing ties at any depth that will fail by pull out. If the frictional resistance developed along the surfaces of the ties is less than the force to which the ties are being subjected. Because in this reinforcing element, we have two faces or two interfaces between the soil above and soil below. We multiply by 2. This 2 comes from two faces of the reinforcing element. LE multiplied by W means area of one face, and sigma prime is the vertical stress multiplied by tangent friction angle, soil tie friction angle. This is basic friction equation. And the safety factor will be equal to this resistance against sliding, Fr, to what? To pull out force, as we just determined for tie force, braking force check. Fr over T. And we can substitute this Fr and T, and the final equation will be in this form. What else we have to do is total length of tie. Total length of tie. As you see in this figure, the 45 plus 5 over 2. This is failure angle according to Rankine theory. So in front of this line BC, the length of this zone don't contribute to pull-out resistance. So we have to consider behind this BC line. So we name this zone as effective length. So we have to determine effective length, but total tie length should be equal to summation of LE and LR. And LE is calculated using this same equation, pull-out equation, taking some value for safety factor. LE is calculated. So LR can be calculated using this triangular relationship. Total length should be the summation of LR and LE. Let us make a summary. Step-by-step design procedure. In step 1, determine the height of the wall, H, and the properties of the granular backfill material, unit weight, friction angle. You don't see cohesion here. You cannot see because our material should be granular material, cohesionless material. Step 2, obtain the soil tie friction angle and the required values of safety factor for braking and pull-out. Step 3, assume values for horizontal and vertical tie spacing. Also assume the width of reinforcing strip, W. Step 4, calculate sigma A according to Rankine theory. Calculate the tie forces at various levels, I mean for every level. And for the known values of safety factor for braking, calculate the thickness of ties. And 7, for the known values of interface friction angle and safety factor for pull-out, determine length. The magnitudes of S sub V, S sub H, T, W, and L, L to obtain the optimum design. By the way, I have to mention this S sub V and S sub H because let me show, the facing elements are prefabricated, and these vertical and horizontal dimensions are constant because it's prefabricated. Depending on the project, these are produced at the concrete factory. External force are the same as other wall types. Yes, these are the same. For better understanding, let us solve an example. Example 13.4. 13.4. A 10-meter high retaining wall with galvanized steel strip reinforcement in a granular backfill has to be constructed. It's a typical reinforced earth retaining wall. And yes, this figure. Parameters are listed here. And we will check external and internal stability. And let us start with tie thickness. Sigma A, but maximum is at the bottom of the wall, can be calculated using this Rankine relationship. So T max, maximum tie force, will be equal to sigma A multiplied by dimension of facing elements. And for tie break, assuming a safety factor, multiplying by T maximum and dividing by W times strength of the element, one single strip. So thickness is 4.28. The rate of corrosion is considered for the lifespan of the structure, and lifespan is given as 50 years. Then the actual thickness of the ties can be increased. Lifespan multiplied by corrosion rate. So thickness 5.53 or more can be taken. Tie length. For tie length, we have to determine effective length, LE, considering pull-out resistance, and LR. This comes from geometry of triangle. Now, for changing that value here for every level, we can make a table such as given here for different depth. The length L can be calculated. Generally, maximum value is taken to be at the safe side. So the maximum value is 12.65. 30 meters can be taken as length. For external stability, the same procedure for overturning, sliding, and bearing capacity will be calculated. Let us start with overturning stability. For overturning stability, safety factor, it's equal to resisting moment divided by overturning moment. And overturning moment comes from sigma A from 0 to h. Actually, this is a triangular distribution. So area of triangle, this equation comes from area of a triangle multiplied by Ka times unit weight, and multiplying with Z over 3, because the wall height is 10. 10 over 3 is 333. So putting into the equation, it's greater than 3, and this is satisfactory. For sliding, 2 over 3 internal friction angle of the soil backfill. This is interface angle between soil and the facing element. Reinforcing strip, and multiplied by normal force. Here, normal force is total weight of this reinforced earth. What is this? This is resisting resistance to sliding. Only force for sliding is PA. We can put just the value. So safety factor for sliding is 3. Check for bearing capacity. For bearing capacity, Q ultimate can be calculated as given here. Soil properties under the wall should be calculated. Please note that we may have cohesion at the natural soil, but at the granular backfill, it should be cohesionless. C cohesion should be always 0, but under the bottom, we may have a cohesion, internal friction angle. So our ultimate bearing capacity should be calculated using cohesion and other factors dependent on internal friction angle. The force or pressure under the soil is equal to weight of the backfill material divided by base area. So safety factor is 19.2. It's very great value, so it's acceptable. We have one more example, two more examples, actually. This example is from, as far as I remember, is from soil mechanics, Craig's soil mechanics book. Details of a cantilever retaining wall are shown in this figure. The water table being below the base of the wall. The unit weight of the backfill is 17 and the surcharge is 10 kilopascal here. X on the surface. Characteristic values of the shear strength parameters. The soil is cohesionless. Internal friction angle is 36 degrees. The angle of friction between the base and the foundation is 27. Here K is used as 0.75 instead of 2/3. Sometimes this is used in some books. Is the design of the wall satisfactory? Let us start with making a table and dividing this geometry into known geometries. And for internal friction angle 36 and friction angle, friction resistance along this zone is 0. This is the case for Rankine method. So active earth pressure coefficients can be taken as 0.26. You can calculate. Please check this result using equation when you study at home. The position of the base reaction is determined by calculating the moments of the forces about toe of the wall. Then for calculations, we have to make this table considering forces and overturning and resisting moments. So for overturning forces, we have horizontal active force. The distribution of horizontal active force is triangular, region 2. And what else? We have a surcharge value above the soil. And this surcharge is used as rectangular distribution, doesn't change along the depth. And this rectangular element is used for this surcharge. For resisting moment, all the weights of the cantilever wall and backfill play a role for resisting. So this backfill is triangular soil, 5 meters. This is height, 5 meters. Width is 1.75, and 17 is the unit weight. Stem and base are two parts of cantilever wall. Stem thickness is 0.3 multiplied by the height 5 meter, and this is the 23.5 is unit weight of concrete. Similarly, for base, 3 meter B multiplied by 0.4 multiplied by concrete. So this is weight. Total vertical force is 212.3, and of course moment arms should be determined. For rectangular elements, just half of the dimension and distance to this point, front end of the wall. After determining moment arms, you can calculate moments, horizontal and vertical, and finally net moment will be calculated. So total net moment divided by total force will give you resultant location for lever arm of base resultant. The resultant acts within the middle third of the base, 1/3 of the base. The factor of safety against overturning will be equal to 2.58. We can determine eccentricity because we just calculated application point of resultant from the midpoint of the resultant, the distance between midpoint and the application of resultant, 1.5 minus 1.15. Eccentricity is 0.35. So maximum and minimum base pressures can be calculated as 120 and 21. We will use maximum value for bearing capacity check. Factor of safety against sliding, because we just calculated here total vertical forces multiplied by tangent interface angle. It's given 27, tangent 27, divided by horizontal force. The force which try to slide the wall is 1.38. Yes, that's all for this question. We have one more question, similar question, only geometry is different and it's given here. The backfill is very limited. When backfill in front of the wall is not thick than the base, such as given in this condition, passive pressure can be neglected. So in this example, we will neglect passive pressure in front. Again, we have a surcharge value, and this surcharge value is the same along the depth, but the earth pressure will increase according to depth, and stress distribution will be triangular, and application points is half of the rectangle for the surcharge and 1/3 of the height for the active pressure. We have a granular backfill and concrete wall, and below the wall the soil is dense silty sand. And soil properties are given: cohesionless soil, C is 0, friction angle, the internal friction angle is given, internal friction angle of soil, and unit weight is given. Friction angle along this base, I mean along this interface between concrete and slab, is also given. Tangent of this friction angle is 0.5 is given, and unit weight of concrete is also given. Let us start with calculation of PA. Of course, before this, we need to determine active coefficient of active earth pressure, and it's dependent on internal friction angle using 30 degree. It's equal to 0.333. So PA at depth 0 is equal to 10 kilopascal. That's resulting from this surcharge. And when we go to bottom of the wall, it will be equal to 58. 48 comes from PA, and this 10 kilopascal comes from surcharge. The best way is to prepare a table like this and divide into areas for area calculations. 1, 2, 3, 4, 5 for 5 region, and also for horizontal forces, earth forces, total vertical force, total horizontal force, moments, resisting moment and overturning moments. After calculating this, safety factor for overturning is 2.23. This is okay. Safety factor for sliding, sometimes, as I said before, sometimes for backfill, smaller backfill in front of the wall, passive pressure is generally not considered. So safety factor for sliding is 1.2. But for sliding, safety factor is taken as 1.5. But the result is less than 1.5, so it's not okay. We have to modify our design to satisfy this safety factor for sliding. Yes, that's all for this semester. If you have questions about today's lecture or all the topics, you can ask. If you don't have question now, you can ask later. You can come to my office or you can write email. You can ask any question. Please study hard. See you at final exam. Good luck.